Hello everyone, my name is Chao Sun. Today I am going to present our work, Single Wheel Procedural Braided Hair Modeling through Braid Unit Identification. Digitalization to create human avatars play an important role in the fields of computer gaming, animated movie, and virtual worlds. Both manual modeling and automatic capturing of hairstyles are challenging because of the complex styling. Modeling different braid patterns with complicated occlusions among braids is a challenging task. Moreover, single-wheel methods have not yet addressed the capture of braids. In this paper, we mainly focus on generating the 3D braided hair model from a single input image. Multi-wheel hair modeling systems usually reconstruct the 3D hair models by first capturing real-life hair images, videos, 3D hair data, then calculating the 2D and 3D orientation fields, and finally, generating hair strands following the 3D or 2D orientation fields. However, the capturing system often requires multiple cameras and a complex setup. On the contrary, the capture systems of single-wheel reconstruction are simple, usually only require one camera. There are mainly two ways to perform single-wheel hair modeling. The first one is by retrieving candidate hair models from a 3D hair model dataset based on extracted features, such as semantic segmentations, 2D or 3D orientation maps. Then refine the candidate hair model to generate the final 3D hair model. The second way is by using deep neural networks. However, those methods require large 3D hair datasets. Who introduced a data-driven method to reconstruct braided hairstyles from input data obtained from consumer RGB camera and a 3D braid patch dataset. However, the quality of the captured multiple hair images and the 3D hair point clouds have a great impact on the effectiveness of the method and the qualities of the reconstruction results. In addition, the scale of the example patches in the dataset also affects the accuracy of the reconstruction and the computation time for patch matching. Our braided hairstyle modeling system only requires a single input hair image. There is no constraints on the wheel of the input image. Moreover, the braid structure information is directly obtained from the image. The system can recover the braid structure without any predefined 3D braid patches or models. Thus, the reconstruction results will not be affected by the scale, variety, and quality of the 3D braid samples. Here shows the overview of our system. The input of our system is a single hair image. There is no constraints on the wheel of the input image. We first segment the braid region. Then we apply our braid unit segmentation method to extract the braid unit information, and divide the hair region into braid region and non-braid region. In the braid region, we recover the 2D braid structure information. In the non-braid region, we extract the 2D hair strands. Then we generated the 3D hair volume based on the silhouette of the hair region. Finally, we project 2D braids and 2D hair strands on the 3D hair volume to obtain the 3D braided hair model. Although a braid is composed of several hair strands, those hair strands are only partially visible in braid images. This is because the braid hair strands overlap on each other. So the appearance of the braid is made of a group of braid units. Variance in arrangement, shape, size, orientation, and locations of the braid units leads to different braid hairstyles. As a basic element of the braid hairstyles, the braid units provide important information about the braid structure. So our braid reconstruction is based on the braid unit identification. Since there is no braid unit dataset available, we create our own braid unit dataset. We download 225 braid hairstyle images from the internet. Those braid hairstyle images contain different hair color, braid length, strand amount, and arrangement. Then we annotate the braid units using a set of polygon points. Here is the overview of the braid unit segmentation system. We treat each braid unit as instance. Then we apply instance segmentation methods to segment braid units from 2D hair images. We apply the mask RCN to segment braid units. After braid unit segmentation, we fit an ellipse to every braid unit contour. The center point of the ellipse indicates the location of the braid units. We use the major and the minor X to represent the orientation of the braid unit. Due to the complexity of the braid structure, there are still a few braid units cannot be detected. We developed an algorithm to recover the missing braid units. After recovering all the missing braid units, we estimate the braid region center curve by quadratic regression based on the center points of all the braid units. A human head typically consists of a large volume of hair strands, and each hair strand has an extremely small diameter, making it very difficult to abstract each single hair strand from hair images. In a procedural modeling manner, it is better to extract a group of K hair strands first, then generate similar neighboring strands to obtain the complete hair strands. Previous research shows that gobble filter is well suited to estimate local orientation of hair strands. We first filter the non-braid hair region with a bank of gobble filters. Then we apply an image enhanced method on the maximum gobble filter response to obtain the enhanced hair strand image. After that, we apply a line tracking technique to obtain the hair strand segments. However, some of the extracted hair strand segments are short, so we apply a grow and connect technique to obtain longer hair strands. Finally, we use a spline with 20 contour points to represent each hair strand segment. Recovering a 3D volume from single image is an ill-posed problem. It is especially difficult in our case, since the braid is usually at the back of the head. To overcome this difficulty, we design a new approach utilizing the silhouette of the hair region to create 3D hair volume. Based on the hair region silhouette, we select equal number of points from the left and right side correspondingly. Then we interpolate 40 points between each pair of adjacent points along the same side. We also fit a straight line based on the first 3 pairs of points from both sides as the center line of the hair region. Then we set image on the XY plane. We select the rotation axis based on the center line. Then the left silhouette and the right silhouette are rotated around the rotation axis towards each other by an interval of 0.01 radians. Then we perform weighted linear interpolation between the corresponding left curves and right curves to generate the final 3D curves. All the points on the 3D curves compose the 3D hair volume. Then we project the 3D hair volume back to the XY plane by orthographic projection. For each 2D hair data point in the 2D image, we find the 3 nearest projected points and calculate the z-coordinate of this point by linear interpolation of the z-coordinates of these 3D points in the 3D hair volume. We will now discuss how the dense hair strands are generated. The projected 3D hair strands are interactively aligned with the scalp mesh. The paths of the braid helical curves are created such that they follow the calculated 3D center curve of the identified braid. We now want to grow dense hair strands from the hair root region of the avatar's head. Our calculated sparse hair strands will act as guides for this process. For each guide curve, we identify the corresponding hair root triangle, which will act as an emitter. We select the triangle closest to the starting end of the curve. The particle system emits dense hair strands from the triangle and trace their paths by following the guide curve. Here we see the dense hair strands resulting from all of the guide curves. For visualization purpose, we use a random color to show the dense strands from each individual guide curve. Now let's discuss how the hair color from the image space is transferred to the hair strands. We create a correspondence between the hair region of the image and the hair root mesh. To do so, the user sets sparse correspondence between the image and the hair root mesh. We associate the surface mesh with the image and warp it to line up the markers. We do so by using the markers as constraints for a Laplacian deformation. The hair root mesh is then texture mapped based on this correspondence. Each dense hair strand gets its color from the hair root mesh through this texture mapping. You can see the final color on this slide. Here we show the reconstruction results of braided hairstyles. The input braid hair image are different in hair strand length, hair color, braid styles, and number of braids. Our results showcase how the procedural modeling is faithful to the shape of the hairstyles and braids. In this figure, the first image in each section is the input image. The second image shows the guide height curves. The last image shows procedural modeling and rendering. Take the left top input image for example. We extract 207 guide curves and generate 187,000 dense hair strands as well as 37,000 braid strands. To sum up, we present a system that can reconstruct procedural 3D braided hair from single hair image. Unlike the existing single hair reconstruction systems, our method starts from hairstyle recognition, partitioning hair regions of different hairstyles. Then take the braid region and other hairstyle regions into separate modeling procedures. The segmentation and analysis of the braid units allowed the recovery of missing braid units as well as the parametric model for the 3D braid. We have tested with several images, and even though it has a few shortcomings and a few manual interventions, it shows that procedural modeling of braids provides a good approximation of the existing hair while still having capacity of easy modification thanks to the procedural model. Our approach has some limitations. Currently, our braided hair reconstruction generates 3-strand braids. This could be improved by adding a braid style recognition method to perform an N-strand braid reconstruction. Also, the presence of accessories like hair clips and bands leads to discontinuities in the braid region. Finally, since the 3D hair volume is based on the silhouette, the 3D shape of the hair is not always faithful to what would be expected. Our approach opens interesting future works avenues. First, we could apply a more accurate hair region segmentation method. Second, we could make the hair color to be consistent with the input image and improve hair relighting with color extraction. Finally, we could improve our work by reconstructing hair even from regions not visible in the image. Thanks for watching.